Okay. So good afternoon and welcome back to CS 159. So first of all, a few announcements. The homework 2 is out and it's going to be due on Thursday. And we will be holding office hours on Discord tomorrow at 3 p.m. if you have any questions. Okay, so now let's get started with today's class, where we will see how we can use the learning MPC to teach an autonomous vehicle how to race. And what we will see is that in order to implement the controller on a real experimental setup, we will need to use historical data to learn a model. And we use a particular strategy to do model learning for MPC, but there is a huge, but there are several other approaches. So I put together a survey of some of the papers which I found interesting. And what we will see is that when we use historical data to learn the system dynamics, there is a discrepancy between the true model and the learned dynamics. And for this reason, when we plan, we want to take into account into uncertainty. So this chapter on model learning will motivate our last topic for today, or maybe for tomorrow, which is how to plan and how to do how to use the model predictive control approach when we have uncertainty. But before starting today's lecture, I would like to discuss a few questions that I was asked offline, because I think that these were very good questions and can be helpful also to others. So what we saw last week we focused on this drone hovering problem, and we computed a control policy by measuring the state of the system and solving a control problem using the batch approach. And at each time t, we solved this batch approach and we applied the first optimal input to the system. And we did this really in a time loop. So we performed this at each time step. And as we saw last week, and as you saw in your homeworks, the optimal control problem that we solve enforced the current state to be within our constraint set, and the current input that we apply to the system to be within the input constraint set. And so whenever we solved this problem and we got a feasible solution, feasibility implied that at a particular time step, our safety constraints are satisfied. And for this reason, we focused on feasibility, because guaranteeing that the control problem is feasible at all time instances implies safety. And so this is the reason why we spend so much time worrying about feasibility. However, I would like to point out that if we relax the state and input constraints, for instance, if we use a slack variable or if we put the safety constraint into the cost, these guarantees are lost. And so this was a good point, a good question I was asked, and I wanted to share it. Furthermore, I was asked a few questions about the stability proofs. So in last week, we saw that the cost of the MPC is decreasing. So J star time T is the open loop cost. And what we saw in our drone hovering problem is that whenever, so as time progresses, our open loop cost decreases. And furthermore, in this specific problem, we saw that our goal was to reach a goal height, which was 0. And this goal height was also an unforced equilibrium point for the system. However, and for this reason, if we reach our goal height, the cost of the MPC controller is going to be 0, because we can stay there without applying any input. And this fact implied convergence. So we have a decrease in sequence and a minimum, which is equal to 0. However, as some of your colleagues pointed out, these conditions are not sufficient to guarantee stability. For stability, we need some more, need to work a little bit more. We need to show that the optimal cost function of the MPC is Lipschitz continuous, and we also need to assume compactness of the state and input constraint set. And I didn't want to go into this because I didn't want to introduce Lyapunov theory. If you have any questions, I think that this book really shows as a rigorous proof of stability. And if you are interested in how to relax these conditions, I listed also another paper which is very helpful and shows that actually we don't need Lipschitz continuity everywhere. We just need it around the origin. Okay, so in summary, in last week lectures, we discussed how we can design the terminal components of a model predictive controller. And in particular, before we move to this slide, actually, are there any questions about stability and recursive feasibility? Okay. So last week, we saw how we can design the terminal components of the model predictive controller. And what we saw is that we need the terminal cost function to be a control Lyapunov function and the terminal constraint set to be a control invariant set. And whenever these two conditions are met, we were able to show safety and stability. And so what we did is that we built on these requirements. And in particular, we saw how we can use historical data to construct the terminal cost function and terminal control invariant set. So I wanted to summarize the strategy that we presented last week in this diagram, where our goal is still to compute a control policy for our drone hovering problem. And here we computed a control action, again, solving a finite time optimal control problem where the terminal constraint and the terminal cost are constructed from historical data. And this is something that we do at each time t after measuring the state of the system. And this is a time loop that we run until our task is successfully completed. And so in this case, for instance, until we reach our goal height. And after completion of our control task, we have an outer loop, which is an iteration loop, where we store the closed loop trajectory, and we use historical data to update the terminal cost and the terminal constraint, which are again used to run the control task once again. And what we discussed last time is that this block here, this finite time optimal control problem block, can be solved with your favorite optimization solver. So here I want to stop for a second to see if there are any questions about this diagram. Okay, so now the question is, we have these two loops, a time loop and an iteration loop. How do we implement this on a real platform? So for instance, how do we use historical data to construct this terminal cost function and this terminal constraint set? Well, it turns out that we can construct these terminal components in a single optimization problem. So as we discussed, in LMPC, at each time t and iteration j of our control task, our goal is to solve a finite time optimal control problem where the terminal constraint set is given by the convex solve of the stored data. So what we can do is that instead of computing the convex solve by hand in an outer loop, we can simply augment our optimization problem, and we can let our optimizer to compute the convex solve. So what we did here is that we replaced our convex solve constraint using a new set of multipliers lambda and the historical data. X stored at time t of previous iteration I. So what we see here is that our predicted state has to lie in the convex solve of the stored data points. And again, we don't compute the convex solve, we let the optimizer compute that. And the advantage of using this strategy is that we can use this multipliers lambda to interpolate our terminal cost. And so what we see with this strategy is that we don't need to perform this inner and outer loop. We can simply solve one unique convex optimization problem to implement our controller. And this is going to be helpful in implementing this strategy on the real vehicle, on the car, on our autonomous racing example. And it's important to underline that this is a convex optimization problem over a sequence of multipliers lambda and input u, and all the performance guarantees still hold. So here I want to stop for a second to see if there are any questions about this reformulation.
Just make sure, what's LICQ?
Oh, linear independence constraint qualification condition. So basically, it's a regularity assumption on the solution of this quadratic program. And yeah, it basically tells you that the gradient of the active constraints are independent.
Okay, thanks.
Yeah. If you want to have more details, I'd be happy like to show you the derivation. Yeah. It's a regularity assumption. It's kind of standard.
I have a question. So you mentioned that the last lecture, like the convex Hall idea works because we have a linear dynamics system. So my question is, if we change the LTI system to LTV, like we add a T on
Yeah.
AT and BT, like I'm wondering if it still works.
Yeah, that's a great question. And the answer is yes, with a caveat. You need to have this terminal constraint set and this terminal and the value function to be time varying. So you want to do at each time t the convex solve of the stored data points across all iterations, but at a particular time step.
I see. Gotcha. So basically, either introducing LTV or introducing finite horizon we will have to add like a time variant terminal calls and terminal constraints.
Exactly. Yes.
I see.
Any other questions on this reformulation? Okay. And this reformulation is really what allowed us to implement this on a real system. And we focused on this autonomous racing problem. So in autonomous race, I mean, our goal is to drive the system, the car, around the track. So we want to reach the finish line in minimum time. And so before showing you how we adapted that problem, so that convex optimization problem, how we use that convex optimization problem to solve the autonomous racing problem, I wanted to show you some results. So how this actually worked on a real car. So here, what we're doing is that we are collecting online historical data that are used to update our controller. Is the sound okay, or is it too strong?
The sound's
Oh,
Just no
okay.
audio.
Oh, sorry. So let me actually reshare my screen then, because I think it's I made a mistake. So share sound. Yes. Okay. So now you should be able to hear the audio. So this is what happened after 10 laps of learning, where we are iteratively updating our terminal cost and our terminal constraint. And so what we see here is that the controller learns how to cut the curves. And we tested exactly the same strategy actually on a real racetrack. So this is a racetrack in Southern California. And this is exactly the same code. The only thing that changes is the first feasible trajectory, which, by the way, in autonomous racing is easy to compute, as we only need to drive the vehicle on the center line of the road at a low speed. And so in this example, we drove the vehicle on the center line of the road at a low speed for 3 laps, and then we iteratively updated our controller. So what we see is that the lap time decreases until we converge to a steady state behavior. And these are, by the way, experimental data. And this is actually, sorry about that. So this is what happened in after 14 laps of learning. So from the side views, you can see that we actually saturate the lane boundaries, so we can safely learn how to race. So now, and this is the closed loop behavior, which is what we saw in the video. So the controller accelerates, then it starts braking right before entering the curve, it starts to accelerate when exiting, and we actually saturate the road boundaries. So we did that also in the chicane, which is the most challenging part of that particular track. So now I would like to show you how we use all the tools that we developed in these 4 lectures to design the controller for this autonomous racing task.
So can I ask a question? A quick question?
Yes.
So it's a very impressive video, but from the sound, from the trajectory, from the from the like a braking system, I can tell it's kind of very close to the limit a braking limit of the vehicle. So my question is, I will assume you have very accurate model for dynamics F, which includes the tire dynamics, some nonlinear stuff. My question is, how do you get this F? And second, what if we have some uncertainties, because it's in general very hard to system ID on F, right? If it's like kind of very nonlinear and very close to the vehicle limit.
Yeah. So we will see that. I'm going to show you how we do model learning here. And the short answer is that we use a linear model. So that's going to be surprising. But we're going to see that in details. So the first step, so the first thing that we needed to do is like a change of coordinates, right? So the track, so the feasible region of this track is clearly non-convex, and this is an issue if you want to do the convex solve of the stored data points. So our first step was to do a change of coordinates. So we represented the position of the car as the distance from the center line of the road and the distance that we traveled along the center line. So with this simple trick, we basically put all our nonlinearity into the vehicle model, and we have state and input constraints which are convex. So the other thing that we needed to do is that we wanted to solve a finite time optimal control problem online, and so as you saw, the historical data entered this finite time optimal control problem, and so we needed to have a systematic way of handling this large amount of data. And so what we did is that we performed local approximations. So let's say that we are given those closed loop trajectory that perform the task. This can be given by a demonstrator, our first feasible trajectory, or also our learning MPC at previous labs. And in general, and so what we did is that we, given a state, we computed the k nearest neighbor to that state, and we performed a local approximation to our safe set, and that we called the local convex safe set. And so what you see here is that the terminal constraint set is going to be a function, or is going to be computed in a neighborhood of a state. So what we are going to do online is that in order to deal with the less amount of data in our optimization problem is that we're going to pick k nearest neighbor to a particular state. And we're going to perform, so the convex safe set evaluated a particular state is the convex solve of the k nearest neighbor to that particular state. And similarly, we perform a local value function approximation. So the local value function approximation is given by the interpolation of the cost to go associated with the k nearest neighbor to a particular state. And this was important because we wanted to reformulate our finite time optimal control problem using only few data points. And so the key idea is that the terminal constraint and the terminal cost are evaluated in a neighborhood of the terminal predicted point that we computed at the previous time step. And as we are, again, implementing this on the real system, we will be also performing system identification online to compute an affine time varying prediction model. And this is exactly the same strategy that you are implementing in your homeworks. And so given these two approximations, so first, we are approximating our terminal constraint set and terminal cost locally, and we are also performing system identification. After doing that at each time t, we are going to solve our problem, compute with a batch approach, and we are going to apply the first element of our optimizer vector to the system. So I wanted to show you how this local approximation to the terminal constraint and the terminal cost is how this strategy works. So in this animation, the red trajectory is our predicted trajectory at each time t. And these data points in green are the subset of data points that we are using to perform our local approximation to the value function and our local approximation to the safe set. And so what we see in this animation is that as we perform more and more laps, the data points are more spread out because we are going at a faster speed, and our controller can plan a trajectory more freely, right? Because our terminal constraint is getting bigger and bigger and bigger. So this was the first approximation that we made in order to implement our controller on an embedded platform. So here I want to stop for a second to see if there are any questions about this animation. Okay, so now let's see how we perform system identification. As Grania mentioned, the system dynamics are highly nonlinear. But what we noticed is that the evolution of the position as a function of the velocity is given by some kinematics equations of motion, which are very simple and known to us because those equations of motion are not associated with the physical vehicle. So in order to compute an affine time varying model, we can simply linearize around the predicted trajectory. However, the key challenge is to understand how the dynamic equations of motion and to perform system identification for the dynamic equations of motion, which are highly nonlinear. And what we did in order to compute an affine time varying prediction model is that we used local linear regression. So at each time t, we're going to compute a linear model which approximates locally our nonlinear vehicle dynamics. And there are a few implementation details which are extremely important for this strategy to work. So the first one is to compute to linearize the trajectory around the previous sequence of optimal inputs. And this is what you have been implementing also in your homework and what we saw last week. The second important point is to enforce sparsity. So we had some knowledge about which states are affected by which input, and this can be enforced in the local linear regression. And furthermore, we want to use only a subset of stored data points. And this is done through this basically kernel function. So this kernel function measures the proximity between the state where we want to linearize and our historical data points. So if a state is far, we don't want to use it as it's not going to help us in building a local linear model that approximates the system dynamics. And here I want to stop for a second to see if there are any questions about this model learning strategy.
I have a quick question. So how come you're enforcing the sparsity? Is that just for the computational reasons or are there other reasons? Because sometimes like I imagine like, it might not necessarily true. Like even if you have an ideal scenario, it might be sparse, but in reality, maybe you have unknown coupling or something.
Yeah, that's a great question. And actually, we enforce sparsity in order to gain both computation tractability. And what we notice is that if we enforce sparsity, then we needed less data points to perform system identification. And so the sparsity pattern actually that we enforced here was kind of like very intuitive. So we know that the velocity is not affected by the position, right? So if you are at curve number 1 or curve number 2, and you're going to accelerate, the next velocity state that you measure will not be affected by the position. So this is the sparsity that we enforced, that the position does not affect the velocities.
I see. Thank you.
Mm-hmm.
I have a quick question. So can you like train on one track geometry and then see how the system performs on a different track geometry, or does it have to be on the same track geometry where you've collected the data and then you're implementing a learning-based controller?
Yeah, that's a great question, and the answer is no. You cannot. You always need to start from a first feasible trajectory for that particular track. With that being said, though, in the MPC lab, there were some people that actually looked into this basically transfer learning and how to use data from one track on a different track. And it turns out that the answer is to look into some reachability properties.
Okay, thanks.
Can I ask a question? So I remember you said that the
the shape. You choose a different frame such that essentially the curve, the shape of the track is somehow embedded in the dynamics. And so does that mean that the dynamics is a time varying dynamics because the shape of the track is changing?
It's not time varying. So we basically did a reparameterization of the system dynamics as a function of the track. So for instance, the curvature now is a state of the track.
How is that reflected in this system ID process?
Yes.
Okay.
Any other questions about this? Okay.
So I have a quick question. I noticed that you, in the previous lecture, had only one starting trajectory, and in this one, you had 3 starting trajectories. Is the reason for the 3 starting trajectories so that you can produce these like local linearized?
Yes, and actually, this is a great point. So what we actually noticed is that we needed more data to do system identification. So one trajectory was really not enough. So this kernel function was giving us like very few data points. Okay. And so as we learned the system dynamics from data, the terminal cost and the terminal constraint from data, we can basically use almost the same code on a different platform. And so here we see a different, so basically the same LMPC strategy, but on a 1 to 10 scale car. And here we run the controller continuously. So every time that we cross the finish line, which is located more or less here, online, we use historical data to update the terminal cost and the terminal constraints. And so here you see that slowly the controller figures out what's a good racing line. And so the lap time decreases every time that we cross the finish line. And in this experiment, actually, it took about 30 laps to converge to a steady state behavior. And so what you see is that at convergence, the controller figures out that in order to minimize the lap time, it has to touch the inner part of the track. And so these are experimental data from our experiment. And what we notice on this top right figure is that the lateral acceleration is basically 1g. So this really tells us that we are pushing the vehicle to the limit. And also in this case, we see that the lap time decreases until more or less we reach convergence. So something that I wanted to discuss in more details is how this system identification strategy works. So in this figure, we see the vehicle, and the points that are highlighted, those are the points which are used by our local linear regression. So again, here we're using a subset of the stored data points. And so here it's interesting to notice that when the controller is in a curve, we use only historical data which are stored in a curve. And when we go on a straight line, we use historical data from the vehicle going straight. And so this really tells us why with a simple model, we can approximate these nonlinear dynamics because we are performing an approximation which is local. So we were able to, again, achieve these results because we have 3 key ingredients. So the first one was a prediction model. Second one was a terminal cost function and a terminal constraint set. So a question that you might be asking is if we do need all these 3 components, or maybe some of those are redundant. For instance, what happens if we remove this terminal constraint set? And so here we are running exactly the same controller that was running on hardware, but we remove the terminal constraint set. And so what we saw is that it crashes. And this it should make sense now because we have seen that in a model predictive control strategy, we really want our terminal constraint set to be control invariant. So when we remove that, our guarantees about safety are violated. And it was nice to see that all this theory that we worked actually it's helpful in our experiment. Any questions on this animation?
I have a quick question that goes back to your comment about reachability and transfer learning.
Yes.
So am I correct in interpreting that reachability and transfer learning is something like, I assume that traveling at low speeds is always going to be safe or something like that? And is there at any point in time, can I possibly slow down safely?
Okay. No, what I meant, I guess I should have explained this like in more details, is that let's say that we have a racetrack where there are like 5 curves, and then we have a different racetrack where there are the same 5 curves which are ordered differently. So then what we might want to do is that we want to take this trajectory, break it down into different pieces, and see if we can connect the pieces so that we get a feasible trajectory for our new track. So what reachability is giving us is that it allows us to see if the chunks of a trajectory that we know is feasible can be connected and used for a new track.
Okay, so I don't want to derail the lecture, but I just have a follow-up question. So there's an assumption that you can always generate an initial feasible trajectory by just driving slowly. And that assumption is probably you already have some working model of the vehicle where you know that at slow speeds you're guaranteed to be safe, let's say, right? So another way of thinking about reachability is not reachability to a state, but reachability to something that reachability to a state, which is slow speeds, where your backup controller is guaranteed to be safe. Is that so? If I use that definition, which I understand is not a set-based definition, perhaps it's more computationally expensive. Like can I always, if my reachability is always something like, can I recover to something that my backup controller can behave safely in? Would that suffice computationally?
Yes, and that would be sufficient to compute the first feasible trajectory that you want to use in here. That can definitely be done.
But that won't necessarily speed up learning because I guess my question was related to transfer learning.
Yes, it wouldn't speed up learning because that trajectory was really slow. So the question is, and really everything started because like we were talking with expert drivers and they were telling us that, oh, I know that like this is that curve which has a U shape. So I know I need to be kind of there when I enter the curve. And then when you talk with them, they are really like piecing together experience from different trajectories. So we started to go in that direction. We saw actually you can speed up learning.
Okay, cool.
I have a question. Oh, sorry. Go ahead, Guanya.
Oh, yeah, just have a follow-up for Isong's question. If you go back to the 3 components in the integrand, and to make total sense to me, like it's hard to transfer the safe set. It's hard to transfer the terminal cost. But I think the prediction model can be transferred to different trajectory, right? For example, if you use a neural network kind of to learn the residual dynamics, whatever, and at least whatever trajectory you're tracking, you can always reuse this prediction model to kind of accelerate like a learning MPC scheme. So my question, I guess, is so why we use a local linear regression instead of use a neural network to regress the whole dynamic, the global dynamics?
Yeah, that's a great question. So I mean, a couple of reasons. So the first one is that like we really need to solve this finite time optimal control problem fast, right? So if you have a neural network in there, how do you solve that problem? I'm not saying that it's not possible. I'm saying just that it's harder, right? Because maybe you want to use MPPI, cross entropy methods. You want to sample trajectories. So we do this on it's not a computationally limited hardware, but it's something that can run on your laptop at 20 hertz. So this is the first reason. The second one is that we really were leveraging this fact that at each lap you do just a little bit better, right? A little bit better. So you're basically overfitting, right? So you're running your controller on almost the same data set that you have before. You're just going a little bit faster. So we didn't need to have a very high expressive function approximator.
Yeah, and make total sense to me. So basically, we don't control the exploration, so it's hard to use something like neural network, which implicitly require like a sufficient exploration in some sense.
Mm-hmm.
That's the final project idea, by the way, for those who are paying attention.
Yeah, and actually here it's something that I think we need to distinguish is the exploration for model learning, but there is also the exploration for value function learning. So this strategy gives you exploration for value function learning, but you're very correct in saying that like we need to modify this to have exploration also for model learning. But really the reason why we focused on this was really to show that when you do this exploration, having this terminal constraint set can be used to guarantee safety. And this was really motivated, of course, when you have nonlinear system uncertainty, the proofs are not rigorous anymore, but like this algorithm is theoretically sound, right? So we have a motivation to design the terminal cost in this way and decide the terminal constraint in this way. And so, okay, so this result, it really shows that we need the terminal constraint set, but now you might ask, why are you doing MPC? You have a terminal cost function, you have a terminal constraint set, why don't you just run Bellman recursion, right? And the reason why we don't do that is because if you run the Bellman recursion, you're not going to learn, right? And the reason is because our value function is approximated on a subset of the state space. And so here we really see the difference between the dynamic programming approaches that we saw in lecture 1 for discrete state and action spaces and this policy iteration strategy for continuous state space. So the main difference is that we do not approximate the value function everywhere. And yeah, so, and this is really the main difference between standard reinforcement learning or approximate dynamic programming strategies and this LMPC approach. And what I want to point out is really the need for a prediction horizon. So in our lecture 1, we showed how to use dynamic programming or value iteration to compute the optimal value function. And so for a continuous problem, what we would need to do is that we would need to grid the entire state space. And after gridding the entire state space, then we can play this Bellman recursion, moving backward in time. And this would guarantee that we converge over the entire state space and we compute the optimal value function. But in order to do so, we need to grid the entire state space. And again, place ourselves in all of these states or these gridded states around the Bellman recursion. What we did is that we gave up basically on optimality, global optimality. We sacrificed that, but we got this computationally appealing strategy where we approximate the value function only over a subset of the state space. And so the main difference is here, optimality is propagated forward instead of backward. And for this reason, we need a prediction horizon that is long enough to learn. So this is exactly what we saw in the previous example. If the extreme case is that our prediction horizon n is equal to 1, in that case, we don't learn, but we can actually, for the linear case, of course, when everything is nice and convex, we can quantify rigorously which are the conditions on the prediction horizon so that we converge to global optimality. And so here I want to stop to see if there are any questions about this. Okay. So in this first part of this lecture, we've seen how we can implement the learning MPC on an autonomous raising experiment. And we saw that in order to do that, we really need to use historical data to learn the system dynamics. However, there are really a lot of strategies that can be used and have been proposed in MPC. So I wanted to kind of give you an overview, and I want to underline this is absolutely non-comprehensive. There are a lot of works that I'm going to skip, but these are some of the works which I believe are important. So first of all, we can characterize model learning in 3 different buckets. So there is these linear words, where our goal is to use historical data to learn a linear system. Then another strategy that is pretty popular is what is called gray box, which is what we used in our experiment. So where we have a known system dynamic, some part of the system dynamics which are known, and some other parts of the system dynamics which are unknown. And finally, we have the black box model. So we're going to assume I don't know anything about my system dynamics, and I really just want to use historical data. So in the control community, really learning this first box is really important. And what people have been working on is to provide finite sample properties for our estimate. So in reality, we cannot use an infinite amount of data to estimate our system dynamics. So what's going to happen is that we need to use a finite amount of data, and we want to characterize what's the error. And this is, for instance, this paper came out of Berkeley a few years ago and really started, I would say, really a new community. So for those of you that have submitted to the L4DC conference, I think this is basically a paper which brought all this community together. So people from the learning community and people from the control community started to look at this problem. And indeed, I wanted to have here some other papers, but I did a quick Google Scholar search, and basically I saw that in the past 2 years, there are about almost 10,000 papers on learning and LQR. And to see that to see what's the difference, I also checked between the year 2000 and 2004. So this is really to say that this is a community that is thriving and people are really, really interested in this problem. And as we will see in a few slides, there are great reasons to be interested in this problem. Here, I wanted to mention other 2 papers, which kind of use a tangential strategies. And so in this paper that came out a few years ago, people looked into multi-step prediction errors. And then this paper that came out last year, actually 2 years ago now, show that actually you don't need to learn a model. You can use only historical data. And so we're going to see how this strategy are implemented to control linear systems, but linear systems are not everything. So people have also focused on gray box approaches, where again, part of the system dynamics are known and parts are unknown. I think that in general, these are the easiest to get on hardware because we have some physical knowledge of the system and we have some parts of the system which are unknown. And if you are really interested in the topic, I really highly recommend this survey paper, which in my opinion is pretty good. And finally, we have the black box community where people want to use historical data to learn the entire system dynamics. And here I want to underline that, again, there are few papers on this problem formulation. So what people recommend is to learn just the increment from the previous state. So we don't want to learn a model that tells us what's the next state. We want to learn a function g that tells what's the difference between the current state and the next state. And this is kind of intuitive, but there are actually a few papers only on this. And so here I would like to stop for a second to see if there are any questions about these kind of 3 big buckets.
Yeah, I have a quick question. In the gray box setting, how important philosophically is it to distinguish between F being linear versus nonlinear?
Yeah, actually, it doesn't make a difference. And this is why I think the gray box word is not used by control theorists and by people from machine learning, because it's really like you cannot prove anything really, or it's hard to prove guarantees about your system. And it's not as interesting as learning the entire system dynamics. Okay, so let's start with the first strategy, and so not all, but like some of these papers basically use regression, and here you can have, if you wish, also a regularizer, or you don't. And the idea is that using historical data, we can approximate our system dynamics, A hat and B hat. And so now what's going to happen is that as we use the approximated system dynamics in control synthesis, we have that there is a discrepancy between the predicted trajectory and the true trajectory of the system. And this difference is going to depend on the error. So on basically how good is our estimate, the initial condition, and also our disturbance. And so this problem is actually challenging because the fact that A and B are uncertain introduces some nonlinearity. So even if we have a system which is linear, we have that the model uncertainty is going to multiply our state. And so for this reason, when we keep propagating, this problem is going to, and so we need to basically over approximate the states where our system might be. And for this reason, the problem is actually NP hard. And that's why people are proposing very different approaches to approximate these sets and to compute safe controllers. And these errors usually are given from statistical learning theory. And so one problem that we have here is that as we propagate forward, these errors multiply. So this makes this problem challenging. So another way of tackling this problem is using to learn linear models for multi-step prediction, right? So what we can do is that we can directly learn a linear model that maps our current state to a state which is 2 steps ahead. So basically, those methods are learning directly those matrices that you guys built in your homework 1 for the batch approach. And so the nice characteristic about this approach is that now we can use statistical learning theory to quantify the errors in the future. So we don't need to propagate the errors. So here we really gain something in terms of computational tractability. Of course, there is no free lunch. We also lose something because we lose the causality between and the relationship between the predicted trajectory.
Ugo, can I ask what you mean by using by statistical learning theory?
Yeah. So basically, like you have regressions, and so what people do is that they either assume or take one data point for trajectory, and then use standard bounds for regression. So right. You know that, for instance, your estimate with this confidence is epsilon far. Sorry, your true model with this confidence is delta far from your estimate with high probability.
Right. I guess I'm saying this could be a good project for someone because usually what the outcome of neural network research is that what people usually mean by statistical learning theory is far too slack. It gives you generalization bounds which are much slacker than what you see in practice. So that could be a right. It technically gives you a bound on the behavior of the system, but it's so slack that it's it doesn't really tell you about how things actually work. But yeah, anyway, that comes up later in the course.
Yeah, but yeah, actually, that's what you just mentioned is a great point because some people don't want to use neural networks for prediction because they don't know how to compute these error bounds. So that actually would be an interesting project. And so that's actually one argument of people that use Gaussian processes, that they say we prefer to use Gaussian processes over neural networks because we get for free error bounds.
Right. Okay. I love Gaussian processes, but I must say that particular statement irks me because you make so many modeling assumptions to build a Gaussian process that your error bounds are dependent on those modeling assumptions being true. And for safety critical applications, if you cannot satisfy those modeling assumptions, then these guarantees are vacuous.
Yeah, I'm an ambassador here, so like I agree, but like the community is really into Gaussian processes. But yeah, I agree with you. I'm an ambassador. We use local linear models, so it's even simpler modeling approach. Okay, so any other question, thoughts, or comments?
I think to me, I feel like the challenge is not from the type of learner, either Gaussian process or here it's like linear matrix. You need a matrix constitution bound. For example, we can use Professor Joe Tropp's theory, or in neural network, we can use generalization bound. I think the main challenge is how we control the data distribution, because all this theory requires ID data of X, but which never happens in control system because it's governed by the dynamics, right? So to me, it's like the more critical part. It seems like how we control this exploration or whatever to make the data kind of a persistent excitation, something like that. Yeah.
Mm-hmm.
I'm not, so yeah, I guess it's also a question like for like the kind of learning MPC. Like if you want to apply model learning, how do you actually control this data distribution? Like is there some general principles in practice?
Isn't I think you're muted. I'm not sure if you were. No. Oh no. Okay. So yeah, I think what I mentioned before is that in order to get around this problem, what you're doing is that we're making sure that like at each lap we improve just a little bit. And so how we enforce that is using the terminal constraint. So because we have the terminal constraint, you cannot go too far from what you did at the previous time step. So that's really how we make sure that we don't use the model too far from historical data.
I have a question, and this is like a very general question, so maybe it'd be better suited to answer later or offline. But this like, I think this philosophy of like solving locally, like the figure you had with the Bellman equation, solving the entire state space versus I think that was like really cool figure to look at. But I'm just curious how like this local, like inherently optimization methods to me feel local because they're like what we're talking about. They're around like a initial trajectory that you grow and you explore about. I'm just wondering what your experience is like in practice. Like I feel like the autonomous car is like an excellent example. You get really impressive results, but like, could you put this on a walking robot? Could you put this like, you know, like what's next kind of in this?
Yeah, that's a great question. And actually like we do have a paper where basically we have a continuation on this on a walking robot. Like it's not a walking robot, it's a simplified model, but like my personal point of view is that whenever things are non-linear, I kind of give up. I gave up on optimality because there is really no way that you can claim optimality other than having some sort of randomness in your algorithm. So you have to have shooting methods. So I think, and this is my personal point of view, I'm okay with guaranteeing convergence to a KKT point.
So one question, so my research, selfish question, but my research, I like the Monte Carlo tree search method. And one perspective on that is you're essentially evaluating the value function iteration, all the relevant states from an existing starting point. So instead of from all points in the state space, you're just evaluating the value iteration for the relevant states for that particular value iteration. And I mean, obviously it's not like very well suited for controls, but it does have this kind of balance of, you know, globalness because it has like a random search and, you know, so.
Yeah, and I think that these strategies should and must be integrated with what we have discussed here, right? So I think there are, I guess this is more general, but I think there are kind of like different types of learnings and like we're gonna see more in Thursday's lecture, but I think there is like something which is skill acquisition. So you have no idea how to do something and you need to explore the entire space. You maybe want to have some randomness, you want to evaluate all possible states. But once you figure out how to do something, then doing local improvements on that is okay. And then once you have figured out how to do optimally, then you want to switch and do it without any computational load. So I think that like what you mentioned is complementary. So it's going to give a good starting point for a method like this one.
Right. Or what I see as like the really cool thing would be to understand how to decompose your global space as a series of, or as like a series of local spaces where you can just run like this method in each of those, and then you explore kind of through these subsets of like where local solutions are valid.
Yes, exactly. That would be basically what you're saying. Use a more globally optimal method to give you better estimate of the value function. I totally agree that that's a direction, and I'm sure. Yeah, I'm sure that this is gonna be used, at least in practice. And this is also similar to what the autonomous car companies do, right? They have usually like a high-level planner, which is like motion primitives, and then that warm start is used in some kind of optimization-based solver, and then you have some PID at the low level. Yeah, I think there isn't one strategy. It's going to be really a combination of a lot of different approaches.
Thanks.
So any other questions? Okay, so the other method that I wanted to discuss is database prediction. And this is also something that has been really popular over the past 2-3 years, I would say. And the idea is actually pretty intuitive and simple. So let's say that we have this figure where on the x-axis we have the time, and on the y-axis we have the output. So let's say that those blue points, these blue dots, are stored trajectory that are given to us. And let's say that now we are at a particular time instant. And in this iteration, we have performed three steps. So we have recorded 3 data points. Now, if the system is linear, we can express the blue dots as and if the system is linear and we can express the blue dots as a convex combination of the red dots, then we know that applying the convex combination of the input that we have in the previous trajectories, then we're going to perform a trajectory which is in the convex combination of the stored data points. And so this is really a simple observation that tells us that if we have a linear model and a bunch of stored data points, every convex combination of stored trajectories can be actuated on the true system. Actually, it's not even convex combination, it's every linear combination can be actuated. And so there is actually some very nice theory, which is called behavioral theory, that builds on this intuition. And basically, behavioral theory tells us that if we have a trajectory U that goes from time 1 to time L, we can build this Hankel matrix, simply shifting this trajectory. And if some conditions on this Hankel matrix are satisfied, then we can express any trajectories of the true system as linear combinations of the columns of this Hankel matrix. And so now you see that this gets really interesting, because what it means is that in our MPC controller, we can replace our model. So we can throw away our model and we can simply use data as our prediction model. So in this deep C, deep enabling predictive control, the key idea is that we replace the model with these matrices of data, and our optimization variables are simply a vector G, which does the linear combinations of this strategy, and this is or these trajectories of these data points. And this is a pretty popular approach that has emerged in the past few years. So any questions about this strategy? And of course, this works for linear systems. There are extensions to when we have uncertainty, but this is really the key idea about this method.
I'm just curious, why is called database prediction? I think from learning's perspective, it should be called non-parametrical kind of prediction, right?
Okay, yeah. I mean, database was here just to underline that there is no model. So you're interpolating data. So here, really what you're doing is that you're interpolating data points to compute a prediction. Okay, any other questions on this? Okay, then I guess we can move to the second category of learning-based approaches, where we have gray box models. I think these gray box models are really mostly used I would say mostly in robotics. And the most popular approaches, again, is Gaussian process. So people have been working on this for a long time. I would say this is the oldest example that I've seen, where people use MPC with a gray box model. And so here, basically, the authors were controlling a drone. So the goal was to drive a drone from point A to point B, and they show that when you don't model this aerodynamics, performance are worse. And also some people at ETH have implemented this strategy on autonomous driving, where basically you have an extremely detailed model of your system dynamics, model from first principles, and then you learn residual. And so here, mostly usually this is just a constant. So you're really learning just a constant that changes over the track. Okay. So the last strategy are these black box models, which are also really popular. And the key idea is basically to use, for instance, deep neural networks. And this is a paper that we already discussed, where the key idea was to learn an ensemble of models, then do trajectory propagation using sampling, and then applying model predictive control. However, as I mentioned, it's not clear, and I think that this is also another research direction, which is sampling-based strategies the best way of doing receding horizon planning when we have deep neural networks? I think that this is still unclear to me. And actually, when we have black box model, we are not forced to use deep nets. So this is a work done by Ivan, which is a student of Izon, where he showed that actually we can also use Gaussian processes to learn a black box model. And what he did is that he actually learned a Gaussian process that spits out exactly the trajectories that you guys constructed in the batch approach. And so the advantage of doing that is that this approach is compatible with standard optimization solvers. So actually this strategy, we were able to put it on a hardware and was able to run at 20 Hertz, again, on a standard laptop, so nothing too fancy. Any questions about these model learning strategies?
I'm just curious, especially in Berkeley, has anyone tried paths in real robots, like walking robots? Like, does it work?
Yeah, actually yes, but there are. So what I've seen is that there are hierarchical strategies. So I guess you have to look at the papers, because when you open the papers, you will see that there is some kind of like model-based RL, but this model-based RL is not end-to-end. So it's not computing the input that is given to the motors. It's computing a reference for a low-level controller, which is hand-tuned. And usually pretty robust. Yeah. At least this is what I've seen. It can be that, yesterday was a new paper on arXiv.
That's it. Are you talking about the Cassie paper by Sergey Peterbiu and
yes.
Yeah.
Yes, and actually I think there is also one paper which is also more end-to-end. So in that paper they had both a low-level controller, a state estimator, and a high-level gate generator. So really DeepRL it's a block. So it's really not end-to-end. So I'm not aware of any end-to-end that takes raw measurements and sends inputs.
Me too. Yeah, me as well. Because if I understand correctly, all this method, they never learn a low-level contraction. It's just more like a online motion planner, online, gate planner, whatever. Yeah.
Mm-hmm.
I feel like there's the obligatory evolution has done it, but anyways.
Yeah. Okay. So this was, I guess this was all for model learning. So what I wanted to talk next is about planning under uncertainty. So I guess I'm gonna start probably, but we're not gonna, I'm gonna motivate the problem. So why? So first of all, why do we need to consider uncertainty when we're planning? So the main reason is that there is uncertainty in the system, and on top of that, we're going to use models which are learned from historical data. And so as these models are learned from historical data, we really need to take into account that what we plan is not what's going to happen in the future. So I want to have a simple example to show you why planning in uncertain environments is hard. So let's say that our goal is to design a controller for an aircraft, and we have our starting point and our goal point. And the forecast told us that there's going to be high wind in some region. So now if we know that the wind is going to be only in the blue region, and if we want to plan a trajectory which is robust, what we're going to do is that we are going to plan a trajectory that goes around the uncertain region, right? And so this can be done, for instance, with a batch approach, the approach that we used in homework 1 and homework 2. But now let's say that we have a different region where there is wind. Again, if we want to plan robustly, we can plan a trajectory that goes around uncertain regions. But now let's say that we have multimodal uncertainties. For instance, let's say that someone told us that like high wind is going to be either in region 1 and in region 2. Then at this point, if we want to plan a trajectory that's robust, again, we need to go around both regions. But now the question is, what if at some point during the flight, we will be able to measure where the regions of high wind are? Okay, and so what we want to do in this case is that we really want to compute a policy, right? So in this case, we cannot plan over open loop trajectories. We really want to plan a policy that drives us into this ball of some radius from the measurement. And then from there, we want to use historical, so we want to use our measurement to decide if we want to take the blue trajectory or the red trajectory. So what this example shows us, that when we plan under uncertainty, we want to plan over policies and not over open loop trajectories. So any questions about this? Okay, so now let's see why this is a problem when we want to design receding horizon controllers. So let's say that our true system is a linear time invariant system where we have some bounded additive uncertainty. And let's say that our nominal model that we use for control is estimated using historical data. So we're going to use an A hat, which perhaps is computed using regression, and a B hat, which again might be computed regression. And these are the information. This is the information that we have to design our model, right? And so our goal is going to be to design a control policy. And what we want to make sure is that when we put this control policy in closed loop with the true system, the state and input constraints are satisfied. And so here we see two main issues. So the first one is that we want safety for the true system, and we have access only to an estimate of our model dynamics. And the second issue is that we want to compute a policy. Okay, so after these 2 weeks of class, you might look at this problem and say, okay, this is easy. I'm going to use the MPC strategy, right? So what I'm going to do, I'm going to plan a trajectory which is robust to all possible disturbances. I'm going to pick a control action. I'm going to apply to the true system. I'm going to measure, update my knowledge about the environment, and I'm going to replan, right? So, and this is going to give you a policy. So now let's see. Let's see how this strategy works in practice. So we have again our example where we want to drive an airplane to our goal state. Let's say that we use this receding horizon idea. At time 0, we are going to plan a trajectory that goes around both regions. We're going to use this trajectory. At some point, we're going to enter this measurement radius, and we're going to see that there is actually only one region when we have the wind. And so at this point, we're going to replan, and we see that it's not clear what we should do. because we already executed part of our first plan. And so you see that basically we drove ourselves to a point that optimality is lost. So the right thing to do was to plan a policy from the beginning, so that we would have been in a more favorable position when we get feedback from the environment. And so here I would like to stop for a second to see if there are any questions about this, this strategy and why applying receding horizon controllers when you have uncertainties might lead to poor performance.
Do you need to know all of the regions of uncertainty before starting, like at the initial condition?
But in this example, yes. In this example, yes. But there are strategies to handle different disturbance support or unbounded support. Of course, when you have, for instance, a unbounded support, then you have to allow from some probability of failure.
Right.
So for instance, if the wind could have been like anywhere in here, then you should relax your requirement, so you cannot guarantee safety.
Okay.
Well, actually, this is a great question. So in general, to guarantee safety, you need to know the disturbance support. So in this case, all the regions where the wind might be. Any other questions? Okay. So one question that you might ask is like, okay, why should I care about this? And so let's say that you want to design your model-based reinforcement learning algorithm. What you're going to do is that you first are going to learn a model, probably use deep neural network, and then you will perform receding horizon planning. And this is usually done without a terminal cost or a terminal constraint. However, the idea is that we use this model to plan a trajectory in the future. We apply the first action and then we iterate. So what you see here is that here we have the same problem. So we plan over trajectories and not over policies. So let's say that your colleague is implementing a model-free RL strategy, and then you want to compare the performances. So before doing that, I think that would be sensible to do is to ask what can go wrong with this strategy. So what can be limiting the performance of your model-based RL methodology. So the first one we already know is the prediction horizon. We know if the prediction horizon is short, we need a value function, a safe set. So with a short prediction horizon, we already know that the model-based RL strategy is not going to perform well. And this we have seen last week. But what we saw with today's example is that planning trajectories is, in general, is suboptimal. And so we should plan over policies. And so here I want to stop for a second to see if there are any questions. Okay. And so these problems that we've been discussing in this class are actually problems which the model-based RL community started to talk about 2 years ago. And those are 2 great papers that I encourage you to read. And what's interesting is that in the model-based RL community, for sure, the terms are way cooler than the one from the control community. So we have the planning horizon dilemma to see the recursive feasibility issue for short-sighted control actions. And we have this meta policy optimization that describes exactly the issue that we saw with the airplane. So these are, again, 2 great papers, which I strongly encourage you to read. And I think that this class really gave you all the tools to understand these problems in model-based reinforcement learning. So actually, it would be also interesting to have like a table that maps a terming control to a terming model-based reinforcement learning. And this is actually something that partially has been done by Professor Bertsikas at MIT. So his most recent book has this cheat sheet to convert from model-based RL to control. So what we are going to do next time, I see that we're running short on time, so I want to just introduce, so what we're going to do next time, we're going to see, first of all, we are going to see 3 papers that describe how to fix this problem when we do receding horizon planning in uncertain environments. And there are really plenty of papers that can be used to fix this problem. I've decided to show you guys only 3 because there are 3 key messages that I really wanted to convey. So the first one is that the problem is NP-hard. So once you have, simplest case, you have a linear system subject to a bounded additive uncertainty, everything is nice and convex, everything is known. The problem is already is intractable. Second, we're going to discuss an elegant approximation. And again, this is my perspective. So I think that this is an elegant approximation. There might be a better one. However, this is one which is used in the control community quite a lot. And the key idea is that we're going to compute control policies that map disturbances to inputs. And so this is kind of like intuitive if we think back to our airplane example, because in the airplane example, our decisions were a function of the disturbance realization. So that's why it's actually a good idea to have a control policy that maps disturbances to actions. However, we're going to see that this is still computationally a little bit expensive. So finally, I have this paper which actually shows what people do in practice. So what people put on the real robots. Yeah, I see that we have a little bit over 10 minutes, but I think that this is a good place to stop because I don't think I can finish the material in 10 minutes. I don't want to rush it.
I have a question about this kind of survey that you've given here. How do you, I'm not familiar with it, but I know that a lot of people are doing like system level synthesis right now. SLS, which kind of reminds me of these like disturbance to input mapping. Can you kind of place it in your stuff?
Yeah, so actually, so it's important to specify which are your assumptions, right? So when you have like a linear system, linear time invariant system, which is known, you have bounded additive uncertainty, then SLS is simply like a different, basically approach of doing disturbance feedback. Well, if you do this disturbance feedback and SLS, the closed loop trajectory that you do, they're going to be equivalent. So the way how you solve this, SLS, you compute the frequency response, basically. Here you do something similar to what you did in your homework 1, which is basically write a big batch approach and then use robust optimization to dualize your constraints. So the tools that they use, it's a little bit different, but the policy that you get is actually the same. Again, when you have a linear time invariant system with bounded additive uncertainty and linear time invariant system, bounded additive uncertainty. If you don't know A and B, then you start making approximations and things are different simply because you have to do approximations. That's a problem you cannot solve exactly. You can solve exactly. We'll see that next time, but you cannot solve exactly using disturbance feedback. And actually, there are quite a few papers on that compare SLS disturbance feedback and actually EULA parametrization. I can share that, but I guess if you, I think actually the title of the paper might be like on the equivalence between, and then they go. But there are quite a few papers that are comparing these different tools.
Okay, thanks. I've actually seen that paper. I think there's that third one that he also talks about, but I forget which one it is. But thanks.
Oh, okay. Yeah, it's from ETH, I think. Right? Yeah, the one I'm talking is from ETH.
I'm wondering if you go back to the last slides, like the subroutine in. Oh, sorry, go ahead.
Yeah. Sorry. So one thing that came in mind. Actually, like mapping. This is something I should have added before, but and we have this in the next slides. But mapping disturbances to actions, it's kind of like newer in the control community. So I guess like around the 2000s was using the control community. But the operational research people, they've been doing this for a long time. So if you want to do scheduling of your inventory, you will map your disturbances to how much you need to buy. And so it turns out that some of, for instance, these tools are borrowed from the operational research community. Yeah, so, sorry, Guanya, could you repeat the question?
Yeah, if you go back to the last slide, in the subroutine in model-based RL, the first step is always learn model. Oh, sorry, yeah, the second step is, I'm wondering, in the second step, can we use something else than MPC? For example, can we use like Bellman recursion or like some other nonlinear control tools in the step 2?
Yeah, that's a great question. And basically, this is what all this like meta policy optimization is about. So the term meta refers to the fact that inside your model-based RL, you have another routine that does policy optimization to solve the finite horizon planning. So yeah, and this is actually I was surprised. This is a pretty recent paper. I think it's like 2019 paper or something like that. Yeah.
I see. So the inner loop can be general as long as it can do policy optimization given the learned model. It should be fine.
Yeah, policy optimization given the learned model over a short trajectory. So basically what they do in this paper is that they have a short horizon, they simulate forward, and they simulate forward the closed loop system where a policy is parameterized by theta, and then they do gradient updates on that theta. But I think it's interesting seeing that like these things, I mean, these are really things that in control people have been talking for really a long time. So it was kind of surprising to see that the first paper is 2019.
Because to me, it's really hard to understand the difference between the routine control community for 100 years, first system ID, then design control with model-based RL. What is the biggest things to make them different? It's kind of problem bothering me for a very long time.
I mean, I think that the difference is really they use deep functions. They use deep neural networks to learn the system dynamics. And then like once you have that, it's really hard to use standard optimization tools to solve the receding horizon problem.
Yeah, I was gonna say the same thing. I think once you commit to using deep learning to learn the model, you have to rethink all your optimization algorithms.
Exactly. But I totally agree with that. But like the lessons that we learn in the control community, those can be used here, right? So we know, for instance, this planning horizon dilemma is something that like is not it's something that like we know exactly. We've seen in this class, right? We've seen like, oh, if the horizon is too short, we're gonna be infeasible. And the other thing is like if the horizon is too long and I plan over open loop actions, that recursion that we saw for learning linear models, like this uncertainty set that keeps growing and growing and growing, you're gonna have that also in this deep RL.
I think one of the things, and maybe this is more a commentary about research communities overlapping and diverging and then re-overlapping again 20 years later, is one thing that certainly speaking as someone who's a machine learning person trying to read control papers, one thing that's not clear is how much is been sort of specialized to linear systems and what is like a fundamental sort of issue that's orthogonal to whether or not it's a linear system. And perhaps in the controls community, these things are just somehow so ingrained and just understood. But from someone outside looking in, it's hard to tell. And then you see these papers in the reinforcement learning community where it seems like some of these issues are already looked at in the controls community, and I think that's true. I think one of the challenges in general when different communities diverge for decades, really, and then reconnect, is that what is actually fundamental versus what are, at least under some perspectives, like linear versus nonlinear models, just the detail of the model design. That's hard to tease out, and that's why some of these papers that are maybe a bit redundant start popping up.
Yeah, so I think that this is actually a great point, and it's something that I wanted to emphasize. I didn't do, but I think at some point I wanted to write a paper about it. But my main point of view is that if you have something that works for constrained linear time variant systems, then it's something that is going to work for nonlinear smooth systems. And so, and this has been like a guiding principle for everything that I've done, which is I try to have something that works for linear time variant system with steady input constraints, because I know that that is going to generalize in the real world. But I totally agree that when you, for instance, read a lot of these LQR papers, when you see that these papers are based on the Riccati equation, you know already from lecture 2 that like those methods will not even work for linear systems which have constraints. So you have to rethink this method from the ground up. So basically, like you can take these papers, and if you want to solve the problem with constraints, you should restart from scratch. And I think that actually there would be like a huge value in saying, if works for linear time vary with constraints and uncertainty is gonna work on the true system. And this is why that approach worked on the real car, because it was, those were the assumptions that we started from.
Seems like a great paper. I'm looking forward to reading it.
Yeah, I mean, if you want to help, I don't know what's the community. I mean, I know the control community wouldn't care, because I think there is an assumptions and there is a theorem, and that's the paper, right? So I think there is for sure like a lot to learn from this community, which also like I'm kind of entering to, hopefully, is that they really care about solving real problems. So which is something that I really appreciate.
So actually building off Guanya's comment about model-based reinforcement learning, and once you have a model which has this, so the ID part is separated from this control part, right? And analysis, I guess, is subtle, but once you have an ID'd model, what prompts you to use MPC particularly? I've always thought of it as one of the more straightforward way of incorporating constraints. And I can't think of any like general way of incorporating constraints other than MPC as the controller. Would you say that that's also like one of the main advantage of MPC over like, any other controller, out there?
Yeah, I mean, that's why actually, MPC is like one of the few control methodologies that made it like to production. So if you buy like now a Ford car, there is an MPC which is running on, and then the reason is because it can handle state and input constraints. But again, my point here is that when you have this, let's say that even if you decouple, now you have like this system ID that you've done, and like you want to do receding horizon control. Doing what we are doing in the homeworks, for instance, propagating this open loop sequence of actions, it's gonna be okay, it's gonna be fine, but you will gonna lose massive performance. Because ideally you would like to plan over policies. So you would like your plan to be able to account for what's gonna happen in the future.
I see. So it's really this kind of prediction that helps, that gives you a massive advantage. Is that what your point is?
Yeah. So if you have a model and the system is deterministic, right? If there is no uncertainty, what we have seen so far is going to be, I think, very effective, because you plan something in the future and maybe you have little uncertainties, but on average, what you plan is what you are going to do, because you have little uncertainty. So now what's going to happen is that when you have a prediction model which is really uncertain, you have a very high bias, for instance, in your model, then what's going to happen is that what you're going to predict is going to be really off from what you can do. And then in that case, what people usually do is that they robustify. And so they robustify versus all possible things that might be happening. But this robustification is done without considering feedback. I guess this is the example, right? So if you are here at the starting point and you know that there's going to be wind either in this part of the state space or this part of the state space, if you want to plan a trajectory that is robust, you're going to go around, right? But when you apply this in closed loop, you're going to get here, you're going to realize, that the wind is actually only in region number 2. And then at this point, it might be pointless to try to go down, right? At this point, it might be that the best thing that you can do is simply to stick with the trajectory that you plan. But here, my point was that if you would have planned over an horizon using a policy, maybe your controller would have realized that the right decision was to go straight and then commit to going up or down.
Okay, thank you.
Yeah.
Yeah, this is a very standard problem that arises in the operations research community. For scheduling and queuing, airline traffic control, warehousing, etc.
Yeah, so actually, like when we take airplanes, this is how they make decisions. That this is how they plan, so that they consider uncertainty. But the fact is that when you consider uncertainty, that the planning problem becomes way harder. And what we will see next time is actually it's non-polynomial time. And so it's not clear how to incorporate these strategies in a controller that runs in real time.
Okay, I'm going to stop the recording here.